Hello, I'm going to do a brief review of limits at infinity in this video and gearing it in particular to what you need to know in a Calc 2 class, especially when you are determining divergence and convergence of series. So when we have a limit as x approaches infinity, so I'm dealing with functions now, as x approaches infinity of x squared plus 2x plus 3. The way that we want to look at this is, even though this is a polynomial, a second degree polynomial function, if we take a look at what is happening to each term as x gets infinitely large, that will help us to come up with a strategy on how to look at a function and know right away intuitively, without doing a lot of algebra, what is happening. So as x gets infinitely large, this term 3 is just a constant. It stays 3. No matter how big x is getting, 3 is always 3. So as x is getting infinitely large, 3 is just staying 3, and so it doesn't affect the outcome much, because infinity plus 3 is still infinity. Well, 2 times x is getting infinitely large. If we look at just this term right here, as x is getting infinitely large, we're just multiplying infinity by 2. So 2 times infinity is infinity. When we look at this term, what we're doing is we are squaring x. So when x is getting infinitely large, we are squaring those numbers. Well, if you take a look at all 3 of these terms and what their influence is as x gets infinitely large, you'll notice that the highest power term always predominates, is always what I call the most powerful term. Because the larger and larger x is getting, this term is getting larger faster. As an example, if we just let x be equal to 1, 5, 10, 100, 1,000, all right? And so we have our 3 terms. We have x squared, 2x, and 3. Well, when x is equal to 1, x squared is equal to 1. I'm just looking at each term separately now. When x is 1, we have 2, and this is, of course, is 3. When x goes up to 5, 5 squared is 25, 5 times 2 is 10, and 3 is 3. When x is 10, 10 squared is 100, 10 times 2 is 20, and 3 is 3. So you can see already that the x squared term is getting larger a lot faster than the other terms. When x is 100, 100 times 100 is 10,000. 100 times 2 is 200, and 3. Well, 1,000 squared is 1,000,000. And then 1,000 times 2 is 2,000, and 3. So by the time we get to x just being 1,000, x squared term is already at 1,000,000, the 2x term is only at 2,000, and 3 is 3. So in other words, the x squared term is the most powerful term. It is getting infinitely large faster than the other terms. That's important to know in most of our strategies that we use when evaluating limits. So, as an example, let's say we have a rational function, x squared plus 5x over 3x. Okay, or let's make it 3x squared. When trying to evaluate this limit as x is getting infinitely large, we know that in the numerator, the most powerful term is the largest power term, which would be the x squared. In the denominator, the most powerful term is, well, going to be the 3x squared. So in other words, as x gets infinitely large, the 5x doesn't really have that much influence. So what I can do is I can kind of simplify this into x squared over 3x squared. And so x squared over 3x squared, the x squareds cancel out, and I'm really at 1/3. And that is your limit. That's actually the limit. This is also in college algebra how you determine things like asymptotes. And because determining asymptotes is all about limits, except in a college algebra class, you're not really talking about limits. So looking at the most powerful term and deciding what to do from that point on is very important. So if you have a limit as x is approaching infinity of x squared over 2x cubed plus 1, well, the most powerful term in this whole thing is the x cubed. So there's two ways that we can look at this. I can kind of do it the same way I did this one up here, which is say, okay, let's take the most powerful term in the numerator and denominator and just look at those. So that would be x squared over 3x cubed. Well, now we can cancel out some of those x's. I'm left with 1 over 3x. And so what we're doing is we're finding the limit as, whoops, I keep wanting to write n because I've been doing sequences, as x approaches infinity of 1 over 3x. Well, now it's very easy to evaluate this and to see what's going to happen. As x gets infinitely large, the denominator gets infinitely large, and the whole fraction approaches 0. And so another way that we could do this, which is the more analytical way that you're usually taught in a Calc 2 class to do this, is to take the highest power of x and divide everything through by it. So in other words, we're going to multiply by 1 over x cubed, 1 over x cubed. And you've seen me do this in some of my videos. And so what we're doing is we're finding the limit as x approaches infinity of x squared over x cubed over 2x cubed over x cubed plus 1 over x cubed. Well, simplifying this, this is just 1 over x, and this is 2 plus 1 over x cubed. Well, now as x approaches infinity, this x is getting infinitely large, which means this whole thing is approaching 0. Well, the numerator of a fraction is approaching 0, it's going to be 0. Boom. And that's what we already determined the limit to be. So you can do it this more analytical way, or you can kind of do it more intuitively. You can also use L'Hopital's rule. We've learned L'Hopital's rule for finding the derivative of the numerator, finding the derivative of the denominator. I'm just kind of giving you some more strategies to think about how to find limits, because in some of the tests that we have to do in sequences, you have to determine a comparison series. And so this kind of ties in with that sometimes. Here's another good example where just doing it intuitively may be helpful. So what if we have the limit as x approaches infinity of x to the 5th over e to the x? Well, coming up with an analytical way of doing this is somewhat difficult, right? So probably what we would do is L'Hopital's rule. L'Hopital's rule, of course, you have to have the indeterminate form. And as x approaches infinity, we would have infinity over infinity, which is the indeterminate form, because x as approaches infinity, infinity to the 5th power is infinity, e to the infinity is infinity, and so we have infinity over infinity, which means we can apply L'Hopital's rule. So we would end up with 5x to the 4th over e to the x, right? And we would have 5x to the 4th over e to the x. Well, we get the indeterminate form again. And so we have infinity over infinity. We can apply L'Hopital's rule again. And as you're going to see, we're going to apply L'Hopital's rule over and over and over and over again until we get to a point where we can actually evaluate the limit, which is going to be when we get it down to the form 1 over e to the x. And so as the denominator is getting infinitely large, this whole thing is approaching 0. There's got to be a better way of figuring that out without going through L'Hopital's rule about 5 times. And there is. And it's to think about what is the most powerful term. And what I mean by the most powerful term is which term is getting larger faster. So back to the original problem. in this problem, you have a polynomial function, x to the 5th power, and you have an exponential function. Now you can go into Desmos or graphing tool and you can see this for yourself. Just experiment, just go ahead and do it in Desmos. But what I'm going to tell you is true, that no matter how large the exponent is in the polynomial function, this could be the 100th power or the 1000th power or the millionth power, eventually, as we get towards infinity, even if this was x to the billionth power, and this is just e to the x, well, this is going to be pretty big, but this is eventually, given enough time, always going to be bigger than a polynomial function. In other words, e to the x grows larger faster than x to the 5th will. It's going to be, ultimately, this is the most powerful term. This is going to get larger than this is. So if this is going to get larger than this is as we approach infinity, that means that the denominator is getting infinitely large and the numerator is essentially, if we had 1 over infinity, if this is getting infinitely large, then this whole thing is approaching 0. Well, as the denominator of a fraction gets infinitely large, the whole fraction is approaching 0. Well, that's essentially what's happening here, because the denominator is getting larger faster than the numerator. The whole thing is eventually going to approach 0. And again, try it in Desmos. See. All right, well, what happens? So the short of it is, without doing anything algebraic, without using L'Hopital's rule, I look at this and say, well, the denominator is growing faster than the numerator. This limit is 0. Well, what would happen if it was the other way around? If we had e to the x over x to the 20th power. Well, now the numerator is getting larger faster than the denominator, so it's going towards infinity. All right, so these are just a few little helpful hints about how you can actually find limits. You can always use the more analytical techniques, L'Hopital's rule, dividing everything through by the highest power of the variable, or you can sometimes just do them intuitively, and sometimes you have to do both. All right, so I'm sure there's much more that I could do. Let me know if there's anything about limits that you really would like me to do a little video on, and I would be more than happy to do that. Meanwhile, I will see you guys in class.